Continuing with section 6 in chapter 4, what we want to look at in this section are the applications using models of exponential growth and decay. So we're going to be looking at equations which are exponential equations. These are a very particular type of exponential equation which will govern many processes in nature, and they're known as exponential growth or exponential decay, such as radioactive decay. That's an example of an exponential decay function. The form of these equations is such that you have an initial amount of a material, and starting at time 0, that material begins to decay due to radioactive emission. So we're going to track that decay over a time variable. We're going to use t, and the beginning amount we're going to call y sub 0. Generally, when you have a subscript of 0, and this is a subscript, anytime it's written down below, sort of halfway below the line, that's called a subscript. When you have a subscript of 0, that generally means an amount that's the beginning amount. So y sub 0 is the amount present when we start keeping track. Time is the variable. And under the proper conditions, which is not really part of this discussion, so we'll just ignore that for now, but let's assume we're using this type of that we have these types of conditions, and therefore we have a model which can be described by this equation. This equation, the amount of the material at some future time equals the amount that was there in the beginning times base E to k times the time. K is a constant. Y sub 0 is also a constant. This equation is actually the general form of both a growth or a decay function. It's a growth function if this constant k is positive, because this side will get bigger as time gets bigger. It's a decay function if this k is negative, because then this side will get smaller as time gets larger. Let's look at an example. This problem will be using that type of exponential growth function that we saw on the previous slide. And this is a problem where we don't actually have the function. We have to build up the function from a set of data given in a table. So here's our data. And for the exponential growth or decay function, there are only two constants. You can match an equation to data using only two data points. That's what we're going to do here. And we're actually told which 2 points to use. We're told to use the points for the year 2000 and for the year 2175. Those 2 points are these two values. We're going to plug these numbers into the equation, and from that determine the values for y sub 0 and k. However, we're not going to use the years for our time variable. Time instead is going to start at 0 for the year 2000. So 0 and 375 will be that point for that year. Therefore, for the other point, instead of 2175 and 1090, we're going to have 175 and 1090. This shifting of the axis just allows us to work with smaller numbers, and that's convenient. It's not required, but it's convenient. The reason we're developing this model instead of just looking at the table of data is that we're asked in this problem to predict when we will have a particular value of the carbon dioxide. And we want to know in what year we will have 3 times the amount in 1951. In 1951, there were 280 parts per million of carbon dioxide. The problem is asking us in what year will we reach 3 times that amount. So here's the form of our function. In this function, we have a y variable and we have a t variable. Y sub 0 is a constant. K is a constant. E is base E, which is a constant. So we have these, we know E. What we need to determine are the values for y sub 0 and k, because y and t are variables. The way we do that is we take those points from the equation and plug them in. So we can take the point when time is 0. At time t equals 0, the number of parts per million of carbon dioxide was 375. That's that point that corresponds to the year 2000. So here we have the value for that year 0. And here we put the year 0 for time 0. Well, if we have k times 0, anything times 0 is just 0. So what we have is e to the 0 power. Anything raised to the 0 power is just equal to 1. So this is just 1. So the right-hand side of the equation just reduces to y sub 0. The left-hand side was 375. Therefore, y sub 0 equals 375. If you look at the table, that would make sense, because in the year we're calling year 0, that was a value, was 375. So that gives us this value in our equation. Now all we need to do is find that value, and we'll have the entire equation. The way we do that is we take the second point for the year 2175, which has a t value of 175. So the value in that year was 1,090 parts per million. We're going to take the value for y sub 0 that we calculated up here, and we're going to put it here. And we're going to put the time, which was 175, in for t. Well, now that we've done that, the only thing in this equation that we do not know is that value k. But this is just an exponential equation. We can solve this equation for k. So do that in the normal way. Divide both sides by 375. And if you remember, the way to solve an exponential equation is by taking logarithms of both sides. Because we have base e, we're going to take the natural logarithm of both sides. And we get this equation. Logarithm of 2.907 is just a number. Divide that by 175, and we get k equals 0.00610. If we take the value for k that we just calculated here, and the value for y sub 0 that we calculated here, plug both of those into this equation here, we get the final form of our model equation to be y equals 375 times e to the 0.00610t. There is our modeling equation. It will be exactly true at the 2 points that we were told to use in the year 2000 and in the year 2175. This is our modeling equation. The next question we were asked was to predict when we will reach a certain value. Well, if we're predicting when, that means we don't know t, we need to calculate t. What we do know is how much. How much is it? Well, it said triple the amount in 1951. The amount in 1951 was 280 parts per million, so we want 3 times 280 parts per million. So that's the left-hand side. Here's our 375E.0061T. So we have an equation now in which the only thing we don't know is T. It's an exponential equation. Solve it in the normal way. That's the value in 1951. 3 times that is 840. Divide both sides by 375. Take the natural logarithm of both sides. Then divide by the coefficient of t. And here I rounded off because would have had an unending decimal. So I get approximately 132t. 132 is the value of t. But t is not the year, it's not the date year, it is how many years since 2000. And so the answer to my question, or the question that was asked, was in what year? That means a date year. So in what year? It's not going to happen in year 132. It's going to happen 132 years after 2000, or it's going to happen in the year 2132, and in that year there will be 3 times 280 parts per million. So a real world type of question that can be answered by using mathematics and using techniques of these exponential equations to find an answer. Another type of problem would be a compound interest problem. In this case, we're going to look at continuous compounding. And if you remember what continuous compounding means, it means that we use an exponential equation. The formula is A equals PE to the RT. A is the amount in the future, P is the amount you're beginning with, base E, R is your interest rate, used as a decimal, T is the time in years. Remember, your interest rate must be in percent per year, time must be in years. So we know what our interest rate is, but I don't see any other numbers here. Where do I get my other numbers? Well, we're double. What does the doubling mean? What it means is that we're starting with this much. We want to know when this will be twice that amount. So when will we have 2 times P? So 2P is what we're going to put in for A. We put our interest rate in here. We have a common factor here and here. We can divide that common factor out. So we just get 2 equals e to that. Then take the natural logarithm. When we take the logarithm of e raised to a power, we get 0.0575 times t. Divide by the coefficient, and we get t is just a little over 12. So for this question, you could answer it more precisely, or you could say approximately 12 years. Generally, when a question like this is asked in the real world, it's not expected that you would give an answer to a precise day. They're really wanting for something in terms of how many years. So again, exponential equation. This time it's in a money question having to do with compound interest. We looked at exponential growth. Now let's look at exponential decay. One place that exponential decay is used is in carbon dating of items. Anything that was once alive has carbon in it. And there's a certain amount of radioactive carbon in addition to the non-radioactive forms. And from this radioactive form, we can determine how long since that substance was alive. It can be plant or animal. As long as the item is alive, then the radioactive carbon is constant at some value. However, once that item dies, that object, that person, that animal, that plant, once that item dies, then that radioactive carbon is no longer being replenished, and so it begins to decay at a known rate. Carbon decays at a rate that's well known. So the equation that predicts that decay is this one. And if you notice, it looks extremely similar to what we just saw. Y equals y sub naught e to the k times t. In this case, our k is a negative number, which indicates its decay. T is how many years since the death of the organism. Y sub 0 was the original amount of carbon present. We don't need to know how much was originally present. We're just looking at the percent change. So this is exponential decay. A problem using this would be one such as this. A skeleton was discovered, and it was discovered in the year 2005. Carbon-14, that's the radioactive form of carbon, done in that year, determined that the skeleton had 3/4 of the carbon of a living woman. So they knew how much carbon-14 a living woman would have in her body. They measured the amount in the skeleton and found that it was 3/4 of what a living woman would have. Based on that, you can determine approximately the year in which the woman having that skeleton died. The way it's done is we use the model that we saw on the previous slide. And what we know, the item that we know is this 3/4. We don't have a value for here. We don't have a value for here. But what we have is a ratio between this value and this value. The value currently, which that's what this value is, the current value, is 3/4 of what it was at the beginning. So this is 3/4 of that. Or in other words, 3/4 y sub 0. That's how much the skeleton presently has in it. Y sub 0 then is a common factor that can be divided out. Take the logarithms of both sides, divide by the coefficient, and you get a t. T, remember, is how many years. It is not a date, it is how many years. The question was, in what year did that woman die? Well, this measurement was being done in 2005. It's been 2,366 years since the woman died, so we would have to start at 2005 and go back 2,366. How do you go backwards? You subtract. Well, that gives us a date of minus 361. This is based on the normal calendar, so minus 361 would be 361 BC. That's approximately when that woman lived. So here are some examples of using models that are exponential type models that do predict real world phenomena, answer real world questions. They're very simple to solve, but obviously there are much more complicated forms of these to take other variables into account, other factors. But this it introduces the idea. So these are very useful techniques and are the reason that math is useful for everyday questions.